You realize I am the last talk before lunch, so I won't drag this out too much. To begin with, we had a client last fall that asked us if you could systems. For frequency domain, we usually have 5 or 6 frequencies that the bird transmits on and receives on, somewhere in the neighborhood of 400 hertz up to about 120 kilohertz. 30-meter flight height, and this gives us very high resolution for shallow mapping. Being the frequency domain system, it's got good noise rejection, lots of power in the channels you're mapping, obviously, or in the data you're receiving. Then moving to helicopter time domain, we have a bit lower bandwidth in general than we do with a frequency domain bird. Of course, the time series, we have a 30-meter approximate flight height usually for the helicopter time domain, so we're still close to the ground, so we still get pretty good lateral resolution along the flight lines. Again, we have short TX, RX offsets, transmitter-receiver offsets, just like the frequency domain, and that also helps to give us good lateral resolution in the near surface. I'm going to say it's lower resolution than the frequency domain in the very near surface, okay, right at the top in general. But it has, of course, much deeper penetration than the frequency domain, and that is why, for the most part, everywhere people move to time domain systems is that depth of penetration you can get out of it. Now, kind of the third technique would be a fixed wing time domain. It often has a little bit lower bandwidth than even the helicopter time domain, but much higher flight heights and much longer offsets between the transmitter and the receiver. And that allows us to get deeper, but it does decrease the resolution quite a bit. Both the transmitter-receiver offsets and the flight heights decrease the resolution a fair bit. The nice thing about fixed wing time domain is you are using an airplane. It's faster, you can cover more area, so in general your dollars per line kilometer is probably a little cheaper. Here's just a picture of the different airborne systems. Kind of going around clockwise here, we have a Digin frequency domain, bird, here's a helitim, geotim fixed wing, there's a transmitter wrapped around the aircraft, and the receiver is probably 100 meters behind, VTIM, and then another frequency domain system there with result. So airborne surveys gather a lot of data. They've got hundreds of thousands of line kilometers, translates to tens of hundreds of square kilometers, and very dense long line data sampling, which is great. You get a lot of data out of it, but it also causes a problem in that you have you've got a ton of data, which is also a problem. And it's kind of exacerbated in an airborne system because for the computational load, every receiver has one transmitter associated with it. So you have to compute electric fields induced in the Earth for every single data point. It's not like some other types of methods. MT, for example, you essentially have to do one forward modeling run on one set of fields, and then all your receivers look at essentially one transmitter. Here is a different transmitter for every single data point. So a while ago we introduced the moving sensitivity domain idea to try and take care of this problem. And the fundamental fact is that an airborne system has a very limited footprint compared to the survey size. So there's no reason to try and forward model the response from geology over here when your helicopter is over here, because there is no interaction. So we just look at a little area. We essentially take our entire survey domain, and you take a little tiny subset of that, and you do all your forward modeling and all your sensitivity computations on that little subset. And then when you're ready to do, when you go to do the inversion, you just map that into a big, sparse sensitivity matrix. This reduces the problem size by tens or hundreds or even thousands of orders of magnitude, which allows us to do full airborne surveys in 3D. And this is a chart kind of showing that. Here's year along the bottom. On this axis is a metric of problem size, just being the number of unknowns times a number of data points, essentially the size of your sensitivity matrix. And you can see as we move along in time, there are algorithmic improvements, but mostly the problem size is increasing due to higher performance computers. and then introduce the introduction of the moving sensitivity domain idea, and suddenly we can jump up 4 or 5 orders of magnitude in the problem size. So in summary, frequency domain versus time domain. Frequency domain, higher frequencies, higher resolution of the near surface. You can't see through conductive overburden with it, and shallow depth of investigation compared to the time domain. You know, less than 150 meters. In many terrains, you may be much less than 150 meters. Time domain, lower frequencies, in general, lower resolution than near surface. However, you can see through that conductive overburden, and you can get much deeper. So let's just combine these two methods into a joint inversion and see if we can come up with benefits of both methods. So the inversion methodology. Well, this turns out to be, it turned out to actually be relatively straightforward to combine this into a joint inversion. You know, really what we have to do is just concatenate some HCs together. You can almost perform modeling and sensitivity computations for frequency domain and for time domain, and you stick them together, and you're done. Okay? There's just one misfit functional, which is composed of different kinds of data, and just one trade-off parameter in the Tikhonov equation, with one stabilizer. Now there are a couple of issues to doing this. You do have to combine them correctly. Especially because I thought I had a little more lighting here, but apparently I don't. Because the sensitivities are very different between the two systems, and the data may be, they're not even measured the same way. One's in ppm and one's going to be in nanoteslas per second or something. So we have to be very careful about how we weight this, so we don't fit preferentially one system or another. We want to fit them both to the error level. And since that is the goal of the inversion, is fitting the data to the error level, we're just going to use the data weight, or the errors, the approximate errors in the data, as our data weights. And so here's an example of SkyTem data. Here's a decay in linear space. We're looking a long line and time decay going down. Linear is the same plot in log. And this is usually what we think of in terms of noise. We're getting down to the limit of the signal-to-noise ratio of the instrument here. This is clearly noise. But there's actually a lot of noise up here too. And by a lot, I have no idea what I mean. Okay, there's noise in there. Sometimes there's a lot, sometimes there's a little bit. But all these things, calibration, tilt, flight height errors, waveform, all these kind of issues propagate into this stuff up here and down here. So for an error estimate for the time domain, we just have the simple error model, which is an absolute error level in nanoteslas, which kind of takes care of the noise floor, the base of the instrument. And then we include another term, which is just a percent of the data. So we basically have a percent error and an absolute error. We square them for every data point. We square them, add them together, take the square root. We're assuming they're independent. And that is a very simple error model, but it seems to actually work pretty well for most of the data sets. So by doing that, now we're kind of taking both surveys and making them on the same level in terms of their error, which is a very physical quantity. We need to do the same thing for the model weighting side, because our sensitivities are going to vary quite wildly over an entire survey area. The near surface, you're going to have very good sensitivity. At depth, you're going to have very poor sensitivity. And if you try to do it without data weights, usually you get shipped things that are too shallow and kind of weird flight line striping and artifacts. So we need to kind of equalize the sensitivities also. And to equalize the sensitivities, what we do is we just weight the model parameters, or we weight the sensitivities by the integrated sensitivities. Okay? And with the integrated sensitivities, we not only include all the physics going on, but we're actually using the data-weighted sensitivities. So not only is all the physics and how sensitive, a small perturbation of your data is to a small perturbation, or go back on that, small perturbation in your conductivity, how much it affects your data. Not only that, but also the error in the data is included in the sensitivities. Okay. So the data weights are included in the sensitivities, and then just use the integrated sensitivities to weight, and that seems to put everything on the same level, and then we can do an inversion, and it seems to work. So it's really pretty straightforward, simple modification to a frequency domain type. So let's just look at it now in terms of a synthetic model study. And I'm just going to jump right into the results here. On the left is the true model. We have a couple of kind of near surface blocks. This is a 3D model. We're just looking at one section, one vertical section. So we got depth, and this is a long line. It is a 3D model. Let's emphasize 5 flight lines and put in 3D blocks, looking at one part of it. Here's a true model. I kind of put in blocks which I thought the frequency domain survey would see pretty well, put in an intermediate one that I thought both would see pretty well, and a deeper one. This is a 100-meter background that I didn't really think the frequency domain would see very well. It's down 150 meters. And then I put in 2 very small resistive blocks, just because those are pretty challenging to see with any kind of inductive method, just a little block on the surface, to see if we can pick those up. Now when we look at the results of the frequency domain inversion only, we see the 2 near surface blocks and kind of the mid-level one. They come out just fine. We really don't get a hint at all of that deeper block. We move to the time domain inversion. We see kind of the opposite thing. We are not resolving these near surface conductive or resistive features at all. They're not in the inversion result at all. But we get the kind of the mid-level and the deep conductor come in very strong. No problem imaging those at all. So of course the next thing is to do the joint inversion. And again, the true model's on the left. And the joint inversion did a very nice job of pulling in all 4 conductive blocks. They're imaged very well. Okay? So we've combined the advantages of both. I still can't see the resistive blocks at all. They're not in there, but that's okay, I guess. I wasn't really expecting them to come out too strong. I was just hoping it was magic, but it's not. So in summary of the synthetic model there, the joint inversion captures the benefits of both the frequency domain and the time domain surveys. We're getting good resolution in the near surface. We're getting good penetration down to get the deeper block, and it's done a very nice job of combining the 2. The other thing we haven't put into this, into the synthetic model here that I'm showing, is any noise of any kind. And you know, the joint inversion, I guess, has a little bit better noise rejection for random errors. But random errors really aren't what I worry about. I lose sleep over it. I lose sleep over the systematic errors, things that are, you know, inherent in your calibrations. And by doing a joint inversion, we're actually able to mitigate those systematic errors a bit, because we've got 2 effectively very independent, well, somewhat independent methods, more independent. I don't know, kind of independent. I guess they're both airborne, yeah, but more independent that should mitigate the systematic errors. So moving to the case study here in Bookpurnong, Australia. What we have is we have an area which CSIRO is very interested in trying to map out areas of saline water. They've got a big problem with over-pumping and over-irrigation in this area. So what they've done is they've taken a small area along the Murray River, and they flew several different kinds of airborne surveys in this area to try and figure out which survey was going to be the best, and then they're going to take that survey and fly it on a, you know, extend it to a much larger scale and try and examine the whole river corridor of what was going on. But the good thing for us was that there are many surveys flown in approximately the same location. Okay? Not exactly on top of the flight lines, aren't exactly on top of each other, but they're flown in the same area, and so we have a great data set to work with here. We're looking at the resolve frequency domain system and the SkyTIM system. And if you're familiar with the SkyTIM system, you'll know that they have a high moment and a low moment. And essentially what they try and do is kind of what we're doing here. They have a small chirp, which has very low power, turns off very quickly, and of course they can get very good early times with that. Then they have a high power waveform, and then they get the later time decays off of that. So they're kind of trying to do a joint inversion, joint interpretation from the early time, very early time, all the way through very late time, the SkyTIM. Now to compare this more effectively with your, to kind of time domain in general, we've actually excluded the low moment data. We've excluded that high frequency bandwidth from this. And we're just comparing, we're just inverting the resolve versus the high moment SkyTIM, the deeper part of the SkyTIM. So as I said, the goal here is mapping saline water. We've got the highlands up here. You can see the farming area. Highlands, they're high for Australia. They're like 20 meters as opposed to the river, which is like 3. But here's the highlands, the farming, and here's the Murray River coming through, and you can actually see salinization all over the place down there on the flats. Lots of vegetation being killed. So that's what they're trying to figure out is where is the salt? Where can we install either pumping or injecting wells to try and redirect some of the salt water, get rid of it. So jumping right into the inversion results here, I realize these are a little hard to see because they're kind of small and it's a large scale inversion, but just we'll go to a cross section view more detailed in a second. But up here we have the time domain inversion. Here we have a perspective view of the frequency domain inversion, and here we have the joint inversion. Our conductivities in this area is very conductive from approximately, that is 0.1, from 0.10 ohm meters up to 100 ohm meters. So very, very conductive kind of area. Just looking at this kind of in perspective view, the joint inversion, the frequency domain inversion actually look very similar at the surface. We're looking at the top here. And you'd expect that. Probably most of the information from the near surface is going to come from the frequency domain inversion. It's got great lateral resolution, good near surface resolution. The time domain and the joint inversion definitely look significantly different in the near surface here, right at the top. But as we go down with depth, we can actually see the time domain is kind of dominating the results of the joint. We're getting bigger conductors down deeper, whereas the frequency domain is under the sea. So let's go to a little bit more detailed view here, and it's going to be a line right through here. We're going to cross the river a few times in our line. You can see here's the Murray River, crosses there, and there. Here's our flight line, or our section line along here. The top inversion result is the frequency domain. The middle one is the time domain only, and high moment only, high power. And then the bottom one is the joint inversion of the two. And you can easily, if you look at it hard enough and squint your eyes, you can easily convince yourself that these are seeing very similar things in the near surface, right? We have a resistor that's showing up in the frequency domain. We have that same resistor showing up here in the time domain. Now they do look a bit different, but we've got the same kind of layer, and that's kind of probably what you'd expect. They're reasonably similar. The time domain is definitely seeing a much stronger conductor at depth, and the frequency domain is just not seeing that. In fact, below this resistive layer right here, we're not seeing anything. But that's getting down there to depth of 60 or 70 meters in an area which has, a conductivity of 1 ohm meter. Okay? So that's hard for the frequency domain to get down. When we go to the joint inversion, we kind of do a good job of combining both the frequency domain and time domain results, but we've combined them into an image which actually has much more coherency at depth than the time domain does. And this interpretation here, it's a weak interpretation, but it's an initial go. We're starting to work on a paper for this. But this is done by Tim Munday with CSIRO in Australia. He has tons of information about this. They've really heavily studied this area. They've got a lot of wells. They've got a few physical tools, methods that have been done over the top. And he's very happy about how this thing looks compared to the frequency domain or the time domain. The other thing that's interesting that comes out of this is joint inversion. We get a couple of layers in, 1, 2, 3, 4 layers from the frequency domain, a couple of layers from the time domain inversion. But when we look at the joint inversion, we've actually got a lot of very thin layers, very finely kind of laminated clays and sands in this area. And I think that looks really, really good. I mean, that looks geologic to me. It looks good. We haven't actually compared it to the wells yet. So, I mean, this could be some kind of calibration problem between frequency domain and time domain that is giving us this layer. So this isn't gospel yet, but it looks really good. There's a lot of very fine layers that are going on in here that you'll never pull out of a frequency domain, or you never be able to pull out of a time domain survey from a surface like that. Okay, so for conclusions, we compared the frequency domain and the time domain systems. Frequency domain, better near surface. Time domain, better depth. Okay. Combining the two into a joint inversion allows us to kind of get the get a good geologic image from the near surface all the way down to the bottom of the time domain, and also probably does a good job of suppressing some of the systematic and calibration errors that are going to be inherent in any system. I think the joint version of the field data definitely looks better than either the frequency domain or the time domain independently. And this also allows us to have another method where, say in Nevada, there's probably a lot of time domain being flown currently. There's a lot of legacy frequency domain around. And we can certainly look at this, reevaluate, and try and get a better understanding for some of the more mature mining areas by combining these two things together. And there's actually no reason that you have to plan the survey to do time and frequency domain together. They could be 30 years apart and have orthogonal flight lines. That's fine. It's 3D inversion. You don't have to worry about coincident points. I'd like to acknowledge CSIRO and Tim Monday, who provided the data and have given us quite a bit of help working with it. TechnoImaging for support and permission to publish, and also sending. There you go. It's lunchtime.